Okay, so everyone clear what we're doing? We're starting on page 38, section 4.1.
Yep.
So here's the bad news. It's always bad news. Well, I'll give you the good news. Maybe it's good news. The test we just took last week is probably the easiest test we're going to take, which for some people that might be bad news. But the one on 4 and 5, there is no argument. The chapter 4 and 5 test is definitely the hardest test we're going to take. People pretty much tell me that as long as they're breathing by the time they finish the 4 or 5 test, then maybe they'll be okay. I tell people, as long as you're passing the class by the time you finish, you might still not do well on that test. It's really hard. It's going to take a lot more practice than some of you are used to really understand it. You also want to ask a lot of questions. Don't just copy everything down I'm doing, because then when you go to look at it later, the whole idea is, can I do this on the exam, not can I copy what Jill wrote? Am I understanding it? The good news is 4.1 is not bad. 4.1 is doable. 4.2 is okay, and then all of a sudden, boom, you get slammed in the next class. So a little bit of a warning. So I'm going to start on page 38, 4.1, talking about probability. Probability. A lot of you have heard probability. You've actually seen some probabilities without knowing that's what it was. It's something that represents how likely an event is to happen. Like, for example, how likely is it to have 2 big hurricanes within a week of each other? Right? Pretty unlikely, right? We keep hearing about how unusual that is. Like one of them was a 1 in 500 year storm, and we had 2 of them within a week, so that's pretty rare for that to happen. So the reason we care about probability is we want to know how rare something is, because if it is rare, but then it still happens, we should probably investigate why. And that's the rare event rule on the top of page 38 there. It says, if under a given assumption the probability of a given event is extremely small, the assumption must not be correct. So if I assume, we could get into a nice debate here. If I assume there's no such thing as climate change, right? And therefore, you know, these hurricanes aren't going to happen that often. I know I'm getting political. Then we have 2 of them in a row. Then maybe that assumption that there's no such thing as climate change might not be correct. I could be wrong. I'm just saying. But those are the things we want to consider. If something happens that's rare, you want to think that maybe your assumption might be wrong. Or if I have a fancy quarter, and I assume it's a fair quarter, one I picked out of my pocket, and I flip it 100 times and 99 of them are tails, my assumption that that was a fair coin should probably go out the window, because it's very unlikely that that would have happened. Okay, what I mean by that? That's what I mean by the rare event rule. And rare events are things that have small probabilities, small likelihood of happening. Okay, so let's talk about probabilities. They are always fractions or decimals between 0 and 1. 0 is the smallest possible probability. 0 is right underneath there. That's the probability for something that's impossible. The probability that my car didn't start today that made me late to work is 0, because I was here on time. 0. The probability that you won the lottery yesterday?
0.
Pretty sure it's 0, unless somebody has some big news for us, right? 0. It didn't happen, unlikely. 0 is impossible. So that's the most extreme, and 1 means it's certain. Certain, like it's spelled. I like to think of it as guaranteed. The probability that I have a blue pen in my hand right now is 1. We're guaranteed I have a blue pen in my hand right now. The probability that there's at least 1 person in the room wearing a hat right now.
1.
1. I have 2 people wearing hats actually, but the probability is 1 because it's guaranteed that it's true. Guaranteed it's certain to happen. Think of them as percents. A lot of people like to think of this as 0% chance and 100% chance. 100% is guaranteed. If you think of probabilities as percents. Anything in between is fair game for a probability. The closer the number is to 0, the closer it is to impossible. And the closer it is to 1, the closer it is to guaranteed. So let's just estimate the probability that I have $11,000 in my purse right now. My purse is pretty big, kind of heavy. How likely do you think it is that I have $11,000 in there?
0.
0? You're sure I don't have $11,000 in there?
Like physical cash?
Yeah.
0.
You're sure?
Well, yeah, because no one's stupid enough to carry that much money around.
Maybe I am stupid enough to carry that much cash though. I agree that it should be something really close to 0.
Should be like 0.1 or something.
0.1 probably isn't even close enough to 0. So the point is, I understand why she wants to say 0, because she's like, why would you have that much money? But there is a chance, like, what if I'm buying a used car right after work today or something? You know, there is a small chance that I have $11,000 in my purse. So if we were to estimate that probability, 0.1, I like where you're going with that, Jenna, but I still think that's too big. That means 1 out of every 10 days I have $11,000. That seems a little high.
1 to 0, 0.
Yeah, maybe really small. I don't know. Like 1, I don't know how many zeros that is. 1 in a million, maybe 1 in 10 million chances. Maybe there's a tiny, tiny hint that it could be true. But that number is very close to 0. No, you can't come up with the actual answer because we don't know the probability. We're just estimating, realizing that a really tiny number means it's almost impossible. Does that make sense? And you guys okay why I threw out her 0.1?
Because it was too close
It's too close.
to the 1.
Yeah, I mean it's closer to 0 than 1, but it's still 0.1 is 1/10. 1 out of every 10 days, I don't have $11,000 in my purse. If I did, I wouldn't bring it to work. And by the way, I don't, so you don't need to go looking through my bag later. Now we know it's 0, now that I've told you and confirmed it. Okay, the probability that you will make it home today without a flat tire. How likely is it that you will make it home today without a flat tire? I'm just estimating.
0.5.
99%.
I heard 0.5 and I heard 99%. So start with the 0.5. 0.5 means there's a 50-50 chance you'll get home without a flat
Well,
tire.
yeah, because there's always road construction and there's always nails on the ground, and so you can't account for whether or not.
True, but if you say it's 50%, that means half the time you go home there's a flat tire and half the time there's not.
Well, living where I do, it's not.
But you see what I'm saying?
Yeah.
50-50 might be a little too small. So he says 99. 99%, 0.99 if we make it a probability, which means 99 out of every 100 days he might make it home without a flat tire. Think of it as 99 out of 100. See, that's a little bit more reasonable. Now, let's say that Kirsty, though, knows she's got really bad tires and she drove through a construction site on the way here today. Then your 0.5 might make sense. But without that information, 0.5 might not be the best estimate. So I think I'm going to go with Hector's 0.99. For some of us, it might be even higher. You know, I got new tires. I can't remember. I think I've had, maybe 3 flat tires in my life. How many times I've driven to work? A heck of a lot more than 300, right? So we might have an even higher number. Who's the only person, or what type of person could say that they're sure that they will make it home without a flat tire?
They're walking.
Someone walking.
Aha, someone who walks? Is that what you're going to say too, Anthony? What are you going to say?
If like someone like would, that doesn't make sense.
You take back your answer?
Yes.
Okay,
Someone
sorry.
on a skateboard.
Skateboard? You
Or
can't
riding
really
the
you
bus.
can't flat tires on skateboards, can you? The bus can get a flat tire though. Can't be a bus.
Well, certain sports cars have no flat tires. I think
Okay,
no
if you
matter
have-
what
yeah,
run
those
over,
certain-
they don't go flat.
Right, so you have, if you A, are walking, or if you have one of those special tires that cannot go flat, then what would your answer be?
1.
What? Guaranteed you'll make it home without a flat tire. If you make it home. Okay, what's next? Probability that you will score a 10 on today's quiz. How likely is it that you will score a 10 on today's quiz?
Depends who you are.
What'd you say?
Depends who you are.
I'm taking anybody's answer. Some of us are more confident than others. Yes?
9.
9?
0.9%.
0.9, he says?
I think 0.9% is bad, I mean, just 0.9.
Is 0.9 your answer?
Yeah.
0.9 means what?
90%.
90%? There's a 90% chance that he'll ace the quiz today?
But the class is
What do you say?
So this, I feel like it's like 0.1, so if it's out of 10, was the quiz out of 10?
The quiz is always out of 10.
Yeah.
0.1? So Jenna thinks it's 0.1. She thinks there's only a 10% chance. That's 10%. There's only a 10% chance that she'll ace it. I think it's probably higher than that. You've gotten some 10s already, haven't you? I think it might be a little low. Now, if there's somebody in here who has done poorly on all the quizzes so far, then maybe you would have a pretty low guess on chances of getting another 10 today. Or maybe you come back with this new drive and you're gonna do better. We can't really say what it is, but it's how likely you think. So this pretty much, if this is Hector's number, think of this as 9 out of 10, 9/10. He's saying 9 out of every 10 quizzes he aces. Jenna's saying 1 out of every 10 quizzes she aces. I'm not gonna argue who's right and who's wrong. I'm more worried about how you would answer it. Who could say 0 for this? Since I told you the quiz was at the end of the class. Who are you pointing at? Oh, Nick?
Yeah.
Ah, I like it. Nick has a 0% chance of getting a 10 on today's quiz.
I believe in Nick.
But why? Why is Nick?
Because he's not.
He's not taking the quiz, so how's he gonna get 10 points? Were you gonna say something?
Somebody that's not here.
Somebody who's not here, right? Same idea. They're not gonna get a 10. Or somebody who knows they're leaving early, right? They're gonna have 0%. So I mean, it depends on your circumstances. Now, what if I give you an extra piece of information? What if I've said that you can work together on today's quiz and maybe even ask me for help? How would that change your probabilities?
Greatly improve it.
Would greatly improve it, right? Maybe it's closer to 1 now, maybe it's 99,
Yeah.
0.99 maybe?
0.98.
0.998, he's like trying to get really close to 1 there. If I give you some other information. So probabilities all depend on what's going on and what other information you have. Right now we're just estimating, realizing that anything close to 0 is something that's almost impossible. And close to 1 is almost, well, exactly 1 is guaranteed, but closer to 1 is almost certain or guaranteed. If you think of them as percents, it makes more sense for most people. Okay, let's do some vocabulary. Before we talk about that vocabulary in the middle of the page, though, let's start with the example so that the vocabulary makes more sense. So I'm going to roll a standard 6-sided die 1 time. So for those of you who have actually seen real board games and you don't just play on your phone and the computers and stuff, they have real things called dice. I'll just show you one sometime. You've probably seen them on digital pictures of them online. How many sides do they have? 4? Some of them have 4, but in general, they usually have 6. And they have numbers 1 through 6 on them, or they have 1 through 6 dots, depending on when they were made. So if I roll those, what are all the possible things I could roll?
1, 2, 3, 4, 5, 6.
1, 2, 3, 4, 5, or 6. We call this the sample space. That's at the very bottom of the page. The sample space. All the possible things that could happen. So put that in there at the bottom of the page there. Sample space. If I list all those things, then my events up above there, like rolling an even number, that's an event. Could I roll an even number?
Yeah.
Sure. There's some even numbers in there. So that's an event. Could I roll a number larger than 4? That's another event. So an event is just something that could happen that consists of some or maybe none of these things in our sample space. Or could I roll a 2? Sure, there's a 2. These are all things that could happen. So going back up to the vocabulary, an event is just a collection of results or outcomes. So the even numbers would be the 2, 4, and the 6. The 4 or larger would be the 4, 5, or 6. And the 2 would just be the 2. So that's an event. A simple event is one that can't be broken down. So even consists of 2, 4, and 6. There's 3 different simple events in there. Simple events is just one thing at a time. So of my 3 events there, which is the only one that's simple? We're only into 2, because there's only one way to get a 2. Right? Where 4, 5, or 6, or even numbers, there's more than one, there's more than one way to get that. And then the sample space we started with, all possible simple events. These are all the simple events. We have 6 simple events here. Now before we flip the page, I want to throw another small example. Let's say there's a family that has 2 children. Let's talk about all the possible ways that they could have children in terms of how many boys and how many girls. A couple has 2 children. How many boys and girls could they have? Like, let's start with boys. They could have how many boys?
2 or 1.
They could have 2 boys. So the first child could be a boy, and the second child could be a boy. Or a boy and a girl. They could have a boy and then a girl. Or a girl and a boy. And those are different. The reason they're different is this case, the boy is older than his sister. So there's an older brother and a younger sister. This one has an older sister than a younger brother. The girl came first. So it makes a difference. And then the other option is 2 girls. Yes?
Have you written this in the sample space?
It's just another example of sample space. It's not for the dice, obviously.
Right, but
It's-
that's where you would.
Right, so
normally
that's
put it.
exactly what my point was. So this is another example of a sample space. Because if a family has 2 children, these are all the possible ways that could happen. That's a sample space for simple events. Thank you for clarifying that. So down there still on the bottom of page 38. You okay there? Just another sample space? Okay, so let's flip over to page 39. Now we have some notation. Capital P means probability. When you see capital P of 2 girls, for example, maybe with that problem we just said, that means find the probability that this family has 2 girls. This part means find the probability of whatever's inside there. Find the probability of, in this case, having 2 girls. We'll talk about how to do that in a minute. So P represents probability. They use capital A, B, and C to be the events. Like A could be the event of the even number, B could be the event of 4 or higher. So there's different events have different letters, just so we can keep them straight. And then this notation here is exactly what I was just talking about.
Percentile?
What'd you say?
Is that percentile?
It's not a percentile, it's a probability. It's find the probability that A actually occurs, which we're about to do in a minute. What'd you say?
Will that be expressed as a percentage?
We write them as decimals or fractions. We usually talk about them as percentages, but we have to write them as numbers between 0 and 1. And to be less than 1, it has to be a decimal or a fraction. And then underneath the P of A in the notes there, let's try to make sense of what it says there. To find the probability of A, it equals, and that's a fraction that's just written all in one line. It's hard to read. I'm going to write it on top of each other so it makes more sense. The number of ways A can occur, and on the bottom, the number of different simple events. This is more complicated than it looks more complicated than it actually is. It's written all stretched out on one line on your paper, but it's really a fraction. So now we're going to actually find these probabilities for the A, B, and C on the front. So when it says find the probability of A, that's the probability of rolling an even number. That's what A was on the previous page. I like to always start with the bottom. How many different simple events are there when I'm rolling my die?
6.
There's 6 total. That's always your denominator, all the different things that could happen. And the top is the number of ways that A can occur. So the number of ways I can get an even number.
3.
There's 3 even numbers here, right? 2, 4, and 6. 3 out of the 6, which we would reduce to 1/2. Which most of you probably already knew. So there's a 50-50 chance. 1 out of every 2 times I'll get an even number on average, right? Because they're either even or odd. A warning. When you're doing these on my stat lab, make sure you read the directions. There's times when they want your answer as a fraction. There's times when they want it as a decimal. There's times when they don't care. But sometimes they're very specific, so make sure you read that so you know which one they want. So that's a number between 0 and 1? Right, okay. So then we want the probability of event B. Which one was B?
Larger than 4.
Larger than 4. I said 4 or more last time. Larger than 4. Larger than 4. Still starting with my denominator, there's still 6 possible things that could happen. How many of those are larger than 4?
2.
2 of them, just the 5 and the 6, right? 2 items in my sample space are larger than 4. 2 out of 6, which reduces to 1 out of 3. Which means that out of every 3 times I roll this die, I should get a number larger than 4. 1 out of every 3 times I roll it, I should get a number larger than 4. It's not guaranteed, but that's on average what would happen. Probability of event C. Probability of rolling a 2. Still 6 options.
1.
There's only 1 2 out of all those options. So that's my answer, 1 6. Probability starts off reasonable. Like, okay, we can have a probability. Why does she say this is so hard? I'm warning you, it's gonna get hard real quick. You're gonna blink and then it's like, whoa, what happened? I wanna add one more in here. What's the probability of rolling a 9?
0.
I heard 0.
Well, how many times do you get to roll it?
Well, I'm rolling it once, and these are all the things that could happen.
Then there's.
How likely am I to roll a 9? She says it's 0, but no one else is speaking up. So is she crazy, or we all just agree with her?
It's a 6-sided dice. You can't roll a 9 if it's a 6-sided dice.
Exactly, she's going to convince you all. It's a 6-sided die, it's impossible to roll a 9. If you wanted to do this notation, well, there's 6 possibilities. How many of them are a 9? 0 of them. Or you could have just said 0 from the get-go because you know it's impossible. Sometimes we're just asking you to calculate numbers which you can calculate, but sometimes the answer is 0 because it's impossible. What if I had said the probability of rolling a number less than 10? Probability of rolling a number less than 10.
Yeah. 1.
I'm hearing 100%, and I'm hearing 1. Because I'm guaranteed, right? Out of the 6 options, how many of them are less than 10? All 6 of them. That's a 1. Guaranteed I'll get a number less than 10. There are a couple extra in there to make sure we're awake. Okay, so right underneath those there, probabilities can be estimated by using what's called a relative frequency, meaning how often something comes up, finding out what % of the time something happens. It's called the law of large numbers. So the example right in the middle of page 39 is talking about, in a recent year, 281 of the 290,789,000 people in the U.S. were struck by lightning. Estimate the probability that a randomly selected person in the U.S. will be hit by lightning this year. So we know what happened recently. We want to know how likely it is that someone will get hit by lightning this year. What do I want to do with that example? Yeah, Hector?
Take the 281 divided by the 290,
So he wants the 281 divided by that 290 million and some change. But I want to talk about why we're doing that. That's what he wants to do to find this probability. Why? Why are we dividing those numbers? Based on this.
Because it's both of those answers. There's the number of different simple events,
Right, the number of different people that could get hit by lightning, right?
and then the number of people who did get hit by lightning.
Number who could be hit. Right, all people who could have been hit by lightning. And then the top is the number who actually did. Always your total sample space. So my sample space is every single person in the US. The top is how many actually fell into whatever the category is. In this case, the category is hit by lightning. All right, then. So this is an ugly fraction. Let's turn it into a decimal. Hopefully someone has their calculator handy. You could divide that for me. Tell me what that is in decimal form. By the way, I'll warn you, your calculator might give you something weird, which we need to discuss. What do you got, Kirsty?
Well, there's a -7, which means there's 7 zeros in front of the number.
So tell me what it says before that.
9.6633645158.
And then what's it say?
And then -7, so you put.
Does it have an E there?
Yeah.
Does yours have an E?
Mm-hmm.
I'll wait till everyone divides it. Other people might have slightly different numbers here because different calculators can handle a few more digits. But you should have something similar to this. Everyone having something similar to that? This is, so rule number 1. If you divide this is going to happen to somebody on the next exam. And someone's going to tell me the answer is 9.6. Why can the answer not be 9.6? Hold that thought, Kirsty, she's all over it. Someone else? Hector and Kirsty, I got you guys today. I want somebody else to be awake and let me know they know what's going on. What are you going to say?
It's not like a full person, right?
It's not, well, remember we're trying to find a probability.
Oh.
So you're right, it doesn't have to be a whole number, that's not the issue. Yes?
It has to be between 0 and 1.
It has to be between 0 and 1. As soon as I see something bigger than 1, my brain should say, well, that can't be a probability. It has to be 0 to 1. 1 is the highest it could possibly be. So as soon as you see that, the little bell should be going off in your head saying, wait a minute, that's not a probability. And then if you look carefully at the end, you'll see the negative number over here. Do not be the person who tells me the probability is 9.6. It's very wrong. Even if you round it to 9.7, it's still wrong. It cannot ever be higher than 1. So this means to move your decimal over 7 places in the negative direction, which is to the left on a number line. So I have to technically take this decimal right here and start moving it this way 7 places. So if I did that, it would look like 0.000000. 1, 2, 3, 4, 5, 6. 6, 6, 3, 6, 4, 1, 5, 8. It would look like that. Everyone okay how I got there? This tells me to take this decimal, which was here, and just count it over 7 places to the left. That's where it ends up. Put as many zeros in as you need to make it look like that. Now this number is really close to 0, right? Really close to impossible, which we kind of know. How many people do we know that have been hit by lightning? Not very many, right? It's almost impossible to get hit by lightning. People do. 281 people, that's a lot of people. But out of everybody else, it's a very small probability. It is unlikely for someone to get hit by lightning because it's such a small probability. Oftentimes we write this as 0 plus. 0 plus. If you had this problem, say, on my stat lab, it would tell you to put your answer in there and round it to 4 decimal places. If I round it to 4 decimal places, what would the answer be? 0. Just 0. And it's not impossible, There are some people that got hit. Now, it rounds to 0, which is why we often write as 0 plus, meaning it's so small it's practically 0. It rounds to 0, but there is technically a little probability, a small positive number. Yes?
So when would we like write the 0 plus, like how many zeros do you think is like?
Usually more than about 4 zeros, we go ahead and write 0 plus. If this problem, say, was on the exam, as soon as you got to here, you could write this and then just tell me the answer is 0 plus, because you can see that you're moving over and adding 6 zeros. I don't want you to have to write out how many all these digits, right? So quite a few digits there. On the My Stat Lab, you don't have to worry about it because it will tell you exactly where to round, 3 places, 4 places, so forth. In which case the answer would have rounded to 0.
And you want us to write that whole like thing on the end?
Thing on the end.
Like, so
This part?
the zeros and then the 9, 6, 3.
You probably could even just put the zeros in the 9, 6, 6 and stop there, even, because it's still going to be a 0 plus.
Yeah.
The important thing is if you do cut it off, just make sure you round it. I'm more concerned that you know it's a tiny number and not a big number. Because most people are like, well, that's a really big number. No, it's not. It's way higher than 1, which means it can't be right unless you check this. It's actually a very small number. This is going to come up all semester long. People are going to tell me that that's bigger than 0.05. No, it's not. It's not bigger than 0.05. Okay, what's next? Complement. The complement of event A, which we write as A with a bar over it. I know it looks like a mean, but we're talking about probabilities. It refers to the complement. It's all the ways in which A does not occur. A does not occur. Before we go into my example there, let's go back over here. A was the probability of an even number. Can you describe to me what it would be if it was not even?
Odd.
Odd. So the complement of even is odd. Right? Those are complements of each other. So if this was event A with a bar over it would have been an even number, an odd number, or even again, an odd number. And either you're in this group or this group, there's nobody left out. Either you're even or you're odd, there's nothing in between, right? This one was larger than 4.
Less than 4?
Ooh, less than 4?
4 and
4 or less? Does it matter? The first thing I heard was less than 4. Does that take care of is every number here either more than 4
No.
or less than 4? I left 4 out there, right? 4 has to be in there? So 4 has to be in there. So the complement of this one, B complement, would be 4 or less. Because you can't leave out anybody in your sample space. If everyone see the problem if we had said less than 4? The 4 would have been hanging there and he didn't belong to any group. We can't leave anybody out. We don't want anyone excluded. What's the complement of rolling a 2? Not rolling a 2. You get a 1, 3, 4, 5, or 6, right? So complement's just everything else besides the event you're talking about. They get a little tricky as we move on. I'll mention one now and it'll come up next time. What if I talk about the event that everybody in here loves statistics? I claim I'm going to find the probability that everybody in here loves statistics. What's the complement of everybody loving statistics?
Nobody loves this.
Is that the only possible way? Either you all love it or you all hate it?
Some?
Some of us.
Aha, maybe just some of you. How many of you would have to not like it to prove me wrong? Just one. So if I say all of you love statistics, the complement is at least one of you doesn't. It might be only one of you doesn't and the rest of you still do. I can keep my hopes up. Or maybe there's 2 of you who don't like it, or maybe all of you. But it's not all or nothing, right? There's a lot of things in between. So you want to make sure you think about that. That's going to come up again next time. Okay, so look at the example on the page now. We want to estimate the probability that a randomly selected person in the U.S. will not be hit by lightning this year. Over here, we found the probability that they will get hit by lightning. This blue is not erasing very well today. I don't know if it's my eraser or my pen. So what should I do?
Subtract 281 from the big number and then divide that number by the big number.
So she wants to subtract 281 from this large number. Why does she want to do that?
That's the difference.
We want to know the difference. We want to know how many people weren't hit by lightning. Right? That's what we need to know, because the question is saying probability that you weren't hit by lightning. So we have to take our 29789,000 and subtract 281, and you guys are going to do that for me, because I don't have my calculator handy.
It's 2907, like, 2907, 88719.
88719?
Yeah.
Someone agree with him?
Yeah.
What does that number represent? What'd you say?
People that weren't hit.
People who weren't hit by lightning. We agree that's how people weren't hit by lightning? So if I want to find the probability, or estimate the probability that a randomly selected person will not be hit by lightning, what am I going to do?
Divide it by the whole.
Divide that by everybody again. The denominator is always all possible people. So I have my denominator, which is everybody, and my numerator is that number, if I can get it right. The people who were not hit by lightning divided by the total. If you divide that for me, I know it starts off with a bunch of nines. How many nines are there?
4.
4? I heard 4 and 6.
You got 999, 646,
Double check yours, Kirsty. I think there should be 6 nines.
I got 6 9s and then 0, 3 3 7.
0337? Make sure you copy the numbers down right or type them in right. Did I copy the number down wrong? We agreeing with Phoebe's number? Kirsty's double checking hers?
Yeah.
That's really close to 1. I'm really confident that I'm not going to get hit by lightning this year. It doesn't mean I won't, but the chances are really slim that I will. Very small probability that I will get hit by lightning, and a very high probability that I won't get hit by lightning. Almost 1. If you were asked to round this one on my stat lab, it would round to 1. Doesn't mean it's for sure. It is so close it rounds to 1. Questions? Yes.
So would you just conclude with like very likely?
Oh yes, very likely.
Close to 1?
The closer that you are to 1, the more it's very likely, and the closer you are to 0, the more unlikely it is. Which is right where we're going next. We actually have a definition of unlikely because we talk about small probabilities mean something is unlikely, but the definition of small is relative. So the definition that we're going to use for the next few weeks at least is a small probability, anything that's 0.05 or less is unlikely. 0.05 is 5%, 5 out of every 100 times. Anything smaller than that is pretty rare. That's our definition of something that's unlikely. So this number here, definitely smaller than 0.05. This was an unlikely event. This one was not unlikely. I don't think anything else we did over here was unlikely. All those fractions, if you can't tell, you can divide those on your calculator. This is 0.5 though, that's not less than 0.05. This is 0.33. There's nothing here that's less than 0.05, so it's not unlikely for any of those things to happen. And then we need to make a little correction on our page 39 there, where it talks about an unusual event. Remember last time we got rid of the words unusual? We want to talk about significantly high or low events. this over here. If I can get my eraser to work. Maybe. I want to get a workout just pushing on this board. Maybe I should switch to black. Maybe. Come on, the board. Okay. So instead of where it says unusual event, I want to talk about significantly high and low events. Bless you. Well, we're going to add this in there on the bottom of page 39. Significantly low or high values. I'll give you an example of what I mean by significantly low or high. Remember that fancy quarter I told you I found? Found the fancy quarter, I flipped it 100 times, and I got 99 tails out of 100. What's that tell you about my coin? It's probably rigged, right? Because, why? Why do you think it's rigged?
Unlikely to get those results.
It's unlikely to get those results. There is a small probability of actually getting a number that high, getting that many tails, right? X is significantly high. I'm going to call it X for a minute. If the probability of X or higher is unlikely. Let's talk about what I mean by that. So again, look, the coins. I have that quarter that I flipped 100 times. I got 85 tails out of 100. Still think it's rigged if it's 85? Liam's going, yeah, I think so. How many tails do you think I should get? You would think I'd get 50. If I got 51, would you be surprised? Why not? Some people over here say no.
You have a 50-50 chance of getting heads or tails.
50-50 chance. So you would expect half of them to be tails, right? But it's not going to be perfect. So if I had 51 or 52, you'd be okay, that could have just happened by chance. But at some point, you're far enough away to say that that's pretty unlikely to happen, and that's too high. I just randomly picked 85 out of the air. Later on, we'll be able to calculate how likely that is. But 85 tails is a pretty high number when we were expecting 50 of them. So we're saying that the chances of getting an 85 or higher are so small that that's a significantly high number. Does that make sense? And same thing for significantly low. If I only got, 12 tails out of 100, like, oh, that means getting 12 or less would be really rare. It's not just 12, it's 12 or less. That's the important part, or 85 or more. Questions there? We're good? Okay, let's, oh, by the way, rounding at the bottom of the page. We either write probabilities as exact fractions, as I was doing over here, or we usually round them to 3 decimal places. Every once in a while on my stat lab, they'll tell you to round to 4 decimal places. Just make sure you look at the directions. But we usually round them to 3. Let's go ahead and take our break here. I'm going to go see if I can get the correct copies for us. And then we'll come back with a little bit of 4.2, and then we'll discuss our project. Oh, you want to do exams? Let me give you your exams before we go out. Page 42. 4.2. Yes. Oh, I handed them all out. The other ones are still being copied. Well, the ones I passed out earlier have this page on it for now. You could use that. Find 4.2, 42, and you should be good. We're only doing this one page.
Thank you.
You're welcome. Don't let me forget to get it to you at the end of class. Okay. So we did the basics of probability, but a lot of times you're multiplying or you're adding when you're calculating probabilities, which is why the title of this is the addition and multiplication rule. And the first thing is there's a little hole right in the P. At the very top of the page there, Mine has a hole punch right where it has P of A or B. Is your P missing out something? The hole's in the same place? There's a hole there? It should be the probability of A or B. And it's the probability that an event, oh, there's a typo. Event A occurs or event B occurs. For example, I might say, what if I randomly pick someone in this room and they're either wearing a hat or wearing glasses? Wearing a hat or wearing glasses. Raise your hand if you think you fall into that event. Wearing a hat or wearing glasses. So Brian's back here, he's wearing a hat and he's wearing glasses. But Hannah over here raised her hand, she's just wearing glasses. Anybody wearing a hat and not glasses? Oh look, she's got a hat on but no glasses. So you don't have to be both. You could be just a hat, just glasses, a hat and glasses, just one or the other, or maybe both. Really important that when you're talking about ors, it's one or the other, or maybe both. So that's what we're talking about. So I have a little chart here from a previous exam, and I made a list of, I separated by gender and whether or not they scored a C or higher on the exam or got a D or an F on the exam. So there's just little counts there for how many people fell into each category. So for example, there's 28 males that got a C or higher on the exam. And there's 4 females that got a D or F on the exam. So the first question says, find the probability that if I select a person, one person, that they scored a C or higher on the exam. Probability of getting a C or higher. Using what we did earlier, what do I want to start with? Yeah.
Find the hole.
Find the total of everybody. How many total students am I even looking at?
78.
I'm hearing 78. How'd you guys get that? Just add them all up? Someone agree with them, 78? I haven't added them. So if you add all 4 numbers in the table up, there's 78 people in this table. So out of 78, that's always your denominator, the whole group. We want to know how many people got a C or higher. I'm hearing 69. How are you guys getting those numbers? Both these ladies said 69. You're adding all the C or higher together. There was 28 females plus 41 males. Oh, sorry, 28 males plus 41 females. Those are the people in the first row that got C or higher, which is 69 out of 78. I'm going to leave it as a fraction for now. Just want to make sure we know how to set it up. Okay with that? Okay, how about probability of male?
28.
No, yeah, add 3 plus 5.
We still have the 78 total people. And what's going to go on the top? 28?
No, 8 plus 5.
How many total males are in this table?
33.
33, right? There's 28 and then the other 5? These are all the males. This is the total. 33 out of 78. So now look at the next question. Now if I randomly pick one person out of this group, what's the probability that that person scored a C or better on the exam or was male? Hold that thought for a second, Hector. Everyone okay with the question? I want everyone who either got a C or better or was male. What were you going to say, Hector?
You can just add the 5 males that got a D or F on the exam to the first score C or higher.
So I'm not sure what you're adding the 5 to.
The first fraction we got.
Okay, but if I add 5 to a fraction, it's going to go over what?
These are the integer.
It's gonna go over 1.
I can't add 5 because that's more than 1. I'm not sure what you're saying.
So you're adding 5 to the integer of the first.
So here's what I think you're saying. Take the first fraction and add 5.
No.
That's not what you're okay,
He's
it's
saying
good.
add 5 to
I
69.
added 69.
Ah, so you want us to add 5 to 69. We're going to talk about why.
Numerator.
The numerator,
That's what I was
gotcha.
trying to say.
Gotcha, now it's okay, we're communicating now. But let's talk about why he wants to add the 5. So here's, what we're doing right now is what's called the intuitive approach. Intuitive meaning we're just looking at this table, trying to count how many people are in this category. So I'm going to recreate this real quick so I can point at it. C or higher, D or an F. There's my little brief table there. 794? You think there's 74 total? Not 78 total? There's 78 total people.
I think they're saying you add the 5 at 74.
Oh, you're doing the numerator.
Yeah.
Right, so some people already know the number on the top is 74. I want to make sure everybody else knows where they're getting that though. So hold that idea. You already
put it on the bottom.
Thank you. Some people already know the number on the top is 74. I'm not going to write it there until we all understand where it's coming from. So let's look at this table. I'm looking for a C or higher or a male. So how about these 28 people? Are they in that group?
Yes.
Yeah, they're actually both.
It's everybody but the 4.
It's everybody but the 4 is what Kevin's saying. These people are not male. These 41 females over here. But they were a C or higher, so I want to count them. And these people didn't get a C or higher, but they are male. Only have to be one or the other. Right? Remember my hats or glasses, not both? It's everybody but those 4. So if you add those all up, or subtract the 4 from the total, whichever way you want to look at it, you get 74 out of 78. When you have OR statements, you're very often just doing this addition. You're taking these people, plus those people, plus anybody else who falls into our category. Okay with that number, where the 74 came from? Mm-hmm. So let me ask you a question. I just said, when there's ORs, we're doing adding. Why can't I just add these two probabilities, C or higher plus male? Yeah, Kirsty.
Because you're adding the males in double. Because you've already accounted for them in the first probability.
So my question was, why can't I just take these 69 plus these 33? Can you pull that door close, please? Because these guys right here got counted twice if we do that, right? They got counted in the 69 C or highers, and they got counted in the 33 males. So these 28 people would have been counted twice. So another way to do this actually would have been to go ahead and take my first probability and add my second probability and subtract anybody that got double counted, which would have been those 28 people. Do we agree with that? This is the probability of C or higher. This is the probability of male. And I'm subtracting anybody who was both because they got counted twice. That should still end up being my 74 over 78. Tell me it does, please. I can't do it in my head. Yep, 74. You don't have to do it this way. If you're on my stat lab though and you ask for help, they will tell you to use this rule. So look at what it says right underneath, right above the hole punch, the middle of the page. The intuitive addition rule is what we did first. Just count all the possibilities and don't double count anybody. That's how we got these 74 over here, right? We just counted everybody, nobody got double counted. The formal addition rule, the probability of A or B, is the probability of A. There's the probability of a C or better, plus the probability of B, plus the probability of male, minus the probability of A and B, which in this case is male and C or higher. Those are the people that got double counted. I don't care if you do it this way, or if you just do it that way. I just care that you get the right answer. Yes, ma'am? This 28? From right here. So these 28 males that got C or higher got counted as the C or higher group. They were part of that 69. And they were part of the 33 when I counted males. So they got counted here and they got counted here. So since we double counted them, I had to subtract them back off. Is that what you're asking, or no?
Yeah, I just wanna know where the 28 is.
Yeah, so the 28 is everyone who was in both categories, C or higher and male, because they got counted both times. So if I was doing that same analogy with this class, let's say there's 40 of you for the moment, I would first count everybody who had hats. And I see 1, 2, 3 hats, four hats. And then I'd say, okay, there's 4 out of 40 hats. And then I would count everybody who's wearing glasses, and I don't know how many total, I'm just looking real quick, I might miss some of you. 1, 2, 3, 4, 5, 6 people wearing glasses out of 40. So this is the probability you're wearing a hat, plus the probability you're wearing glasses. But what happened?
There's somebody wearing that and glasses.
There's some people who got counted twice. I counted Brian back there twice, because he's wearing a hat and glasses. I think he's the only one doing both. No, double checking. Yes, he's the only one doing both. So I have to subtract him back off, because he got counted here and he got counted here. And then there would only be a total of 9 people that are one or the other, as opposed to the 10. Same kind of analogy. Or I could have just said, raise your hand and counted to 9, and I would have just had everybody, and I wouldn't have counted him twice. So there's 2 ways to approach that. Okay. I think I'm going to stop right there for now.